I'm gonna round this to 5.5, so we don't have to always write all the sig figs here. 5.5 M2. Now another thing I'm gonna do now is factor out the R of E, so that over here I'm gonna have R of E squared, and over here I'm gonna have R of E cubed. So you'll see here what's gonna happen. 1.40 minus 2.367 R squared over R of E squared minus 0.967 R cubed over radius of Earth cubed. So I made it similar to last week where the answer is in terms of the ratio of R to R of E. So if I say, what would your energy be inside of the Earth if you were 0.8% or 8% of the way inside of the Earth? So you would just put here 0.8 or 80% I meant, yeah, 0.8 squared and then 0.8 cubed, then you would just get the answer. So this is the same units as this. GSM2RE, GSM2RE. So I can simply just take this to the other side, bring all this to this side as a minus sign, and then my final answer for U of R is going to be, I'm going to have GSM2RE. I'm going to factor that out. This is all going to be negative when it comes here, and this is also negative. So we're going to add now. We're going to have -1, and then this one is going to be 3 divided by 5.5 times 1.4. So -1 minus 3 divided by 5.5 times 1.40, -1.76. So let's make it 4 decimal places. -1.764. So that's just a number. And then over here, this is going to come out over here, and it's going to be a negative when it comes here. So this is going to be positive. And then 3 over 5.5 times 2.367, 1.291. So that's going to be positive 1.291. And then that one is going to come over there and also become positive. So positive 0.96, no, we got to multiply 0.967 times 3 divided by 5.5, 0.527. And then R over R of E quantity cubed. And then here I could also express it the same way. R over R of E quantity squared, and we are set. So now we can find out what is the potential energy as a function of our inside of the Earth. So if I put R is equal to, if I put here R is equal to big R, the radius of the Earth, so the potential energy is going to equal what? So R is going to equal big R, R is going to equal big R, so you're just going to be left with GSM2 R of Earth times this one plus this, because these are all just 1. So -1.764 plus 1.291 plus 0.527, which gives you, let's see here. Oh, sorry. This one was a plus sign. I just rewrote it wrong. So this one was positive, this one was negative, this one was plus. So when it goes there, it should be minus. So I want to make sure you get a good result here. So -1.764 plus 1.291 minus 0.527, -1. So this whole thing here comes out -1. And what is this thing here? That it should be the potential energy of an object at the surface of the Earth. Because remember, GS is equal to what? GM Earth over radius of Earth squared. Mass of the whoever is standing at the surface of the Earth times radius of the Earth this and this cancel, so you're left with negative Gm Earth M2 over R of Earth. Perfect. So you should check to see that the potential energy is continuous. Okay, it's a continuous function. How about if we put little r is equal to 0? Well, then simply you just have 0, 0, and you just have this thing. So it's equal to negative 1.764 times GSM2 R of Earth. So your potential energy is it's lower than if the Earth was a uniform mass density. So the graph is going to look like this now. For the potential energy, you're going to have a certain potential energy here, okay? And this one's going to look like this. So if this is the potential energy at the surface, this is potential energy, let's put it this way. This is the potential energy at the surface. So potential UR, which itself is negative. So this one is going to be 1.764 UR. Now the uniform mass density, the potential energy looked like this, right? It was 1.5. So why is that? So if we allow somebody to fall, to the center of the Earth, if the Earth is uniform, remember last time I just gave us some number, I said what if the person's energy was negative 100? If it was uniform, this would be negative 150, right? So they would lose 50 joules, and then that 50 joules would be converted into kinetic energy. How about if it's non-uniform? If it's non-uniform, if the person's energy was negative 100, what would their energy be here? Well, just simply 1.764 times negative 100, so negative 176. Negative 176.4 joules. So they would lose 76.4 joules of potential energy, and they would gain more kinetic energy, therefore. So why is that? Well, because for this Earth, more of the gravity is concentrated closer in. So as you're falling, the material that is left there is heavier. So you're getting closer to a heavier object. And so the decline in potential energy is even more, and you'll speed up quicker. Okay? Now I did a little bit further study, a little bit more detailed study for the force of gravity. Remember the force of gravity we got last week? The gravity inside of the planet? We had some function looking like this. 3G over R rho of E 4.73. Then we had minus 3GM. Sorry, we had 3G over rho of E 4.73 R over R minus 2.9 R over R squared. Right? So that was the gravitational field inside of the planet. So remember that F is equal to negative du dr. Okay, and then F is equal to negative mg. Okay, and so if you cancel if you cancel the two negatives, g is equal to 1 over m2 du dr. So basically, if I just get rid of the m2, the g is basically like the derivative of u. So g is like your electric field in electricity, and the potential u is like your v. Okay, so